Third day of probability, we're going to start with what are called two-way tables or contingency tables. We have two things that we consider each to be a variable here that we're showing. One variable is gender, the other variable is the goals of different elementary kids in their daily lives, I guess. So we have that we either are a boy or a girl in gender, that our goals in school or in life are grades, being popular, or sports. That goes into depth about how they conducted this study, the stratified sample. We're just interested in the probabilities. So the probability that a randomly selected student is, now this part right here is huge actually, because it tells us what our sample space is. Our sample space is the entire, well, maybe not the entire student body, but all the students in the sample. So in other words, our denominator for the next three questions will be the 478. Because it says for each of these probabilities, what's the probability that any of these randomly selected students is, and then whatever. So we are using the 478 as our denominator. So in the first one, when it says the probability of a student being a girl, out of the 478 total students, how many were girls? 251. 251. Okay, and then you can either leave it like a fraction or put down your probability. Little hint here on the quiz, for sure, put that fraction. Okay, if you want to give the decimal as well, that's fine. But this helps you get partial credit. Because if you get at least the numerator or the denominator right, I know that you have the right idea, at least either about the sample space in the denominator or what you're interested in the numerator. But if you just put down the wrong decimal, and I don't know how you got it, you're losing more points. Does that make sense? Put the fraction. All right, that was 251. I accidentally erased it. Now, I'm going a little faster because I want to get this whole video done if we can. But a lot of the tables that you'll be given, they'll only give you those numbers. My hint to you is put down those totals, all of them, right away. It takes a second to just add them up real quick, put them in. That's called the marginal distribution there. Those are the marginal distributions. All right? You're going to need them for most of the questions, especially if you're asked, like in this case, we're asked 1, 2, 3, 4, 5 different probability questions. You're probably going to need at least 2 or 3 of those bold numbers in the marginal distribution anyways. All right, the next question says, find the probability that a randomly selected student is a girl whose goal is to excel at sports. So again, our denominator is 478. The probability that we're looking for here is actually an and probability. The probability that a selected student is two things, a girl and, I'm just going to use the word and, a girl and their goal is to be good at sports. So this is an and probability really that we're finding right here. Out of all the students, how many were girls that wanted to excel in sports? 30, right? There's your numerator. 30 out of the 478. That's about 0.0628. Let me know if you have any questions. Did I make a mistake? Good? Yes? I like 4 decimals with probability. I have no reason why. Otherwise, I just usually go to the 10,000ths or leave it as a fraction. Or percentage. So 6.3% you could have too. Any of those are fine. Last one here in this set, we are looking for the probability that we randomly select a student and that student has a goal to excel at sports. So it's just, I don't know why I'm putting the P, but their goal is to excel at sports. That's it. So out of the 478 students, I believe there were 90 whose goal was to excel at sports, right? All right. Okay, questions? So now here's where things get interesting. This next one says, find the probability that a randomly selected girl has the goal to excel at sports. That is not the same as this one. It's not the same. It doesn't say a randomly selected student was a girl who likes sports. It was a randomly selected girl. In other words, that piece of information is given to us. This is our given event, or the probability of being the girl is our given probability. So we are finding the probability really that someone has a goal to excel at sports given that they are a girl. That's what we're finding here. Notice the difference in the wording of this question and question 2 up above. That's the hard part, is knowing, am I doing an and or am I doing a given? Yes?
So when we're doing work, do we have to use the probability notation?
Oh, good question. This is not a stats class. This is not a probability class. We're just kind of introducing some of this stuff to you. As long as you are showing the fraction and your answer, you're fine. You do not need to show all this stuff right here. If you're in AP stats right now as well and you want to practice doing all that stuff, that's not a bad idea. Notation is pretty important in that. Okay, here's why tables are good. What was our given information, or what were we given? That they were a girl, right? So here's the deal. Here's why tables are nice. Because if you have a table, you know you are only interested in that row. By saying, given they are a girl, you just eliminated everything else. So our denominator, our sample space, are just the girls. What's our denominator going to be?
251.
251. And then what's our numerator going to be? How many girls had a goal to excel at sports? Still that 30 from before. But now it's not 30 over the 478, it's 30 over 251. And this simplifies to, or the decimal is 0.1195. Okay, are we okay at that? Now before I move on, I want to remind you, actually I'm going to do it right here. You don't have to write this if you don't want. The other way you could do the probability of, which one were we given? The girl, right? So sports given girl is, we had a formula that we learned yesterday. The formula that we learned said, in order to do this, you'd have to take the probability of the sports and the girl, and then what would I have to divide this by? What probability? The girl, because that's the given, right? Okay, now watch what happens here. If we do this, the probability of sports and a girl, we actually found that already. That's this one right here. And I'm going to just use the fractions here because fractions are where it's at. 30 over 478 over, and now the probability of being a girl, hey, we found that too. Actually, I'm going to use the fraction, the 251 over 478. 251 over 478. So watch what happens here. I got a complex fraction. I'm going to simplify by multiplying by the LCD to cancel those out. Or you can multiply by the reciprocal. Or you could just cancel them because that's how you roll. Watch what happens. You get the same exact answer as what we got before. Formulas are good, but tables are way easier to interpret. Questions on that at all? All right. So then let's find this one. Find the probability that a student whose goal is to excel at sports is a girl. We're looking for the probability that somebody's a girl given that we know that their goal is to excel at sports. Now, what we just did there, do you notice how these two are the same things but like flipped around? That's called reversing the condition. All right? Reversing the condition. And if we have some time at the end, I want to go back. Remember the meatloaf problem that we did yesterday? Like the greatest example ever? We might look at that again and reverse the condition on one of those just to show you how to do it with a tree diagram, if we have time. All right, so how would we do this? Look back up at your table. Let's not worry about the formula here. Let's look at the table. What are we actually interested in as our sample space? What's our denominator going to be? The 90, the sports, right there. That's all we're interested in. What's our numerator going to be? Yeah, that's still 30. So I like these set of questions because they use some of the same numbers over again, but they are in different spots. We're mixing things together differently. So this is 0.333 if I was sick at going to the thousands like I have been. Or you just call it 1/3. All right, so here's where things get real. And you will have a question like this on your quiz. And it will be worded just like this. I'll ask you to find a couple probabilities, and then it'll say, what do you think? Are these independent? It won't be like yesterday's example where it said, do you think these are independent? And then it said, hint, compare this probability to this probability. You need to know what probabilities to compare. Now you have choices here. Now you could actually compare all sorts of things from this table, but look at the probabilities that we've calculated. You either have the choice to compare girl to girl given sports, or sports to sports given girl. You can do either one of those. And if they are equal, then you can say that these two things are independent. One happening doesn't affect the probability of the other happening. Okay? Now, what does equal mean? After talking to some of the AP Stats students today, I think they were pretty hard down on it. It's got to be the exact same thing, which I never really believed in. To me, if it's in, but it depends on the situation too. To me, if it's within a couple of percentage points here, now we're not doing a hypothesis test or anything like that for those of you that are in AP Stats. There's no alpha level that we have. To me, if they're in a few percentages of each other, I would say that's close enough to say that they are independent of one another. All right, so let's compare them, then we'll talk about that even more. So what set do you want to do? It doesn't matter what you want to do. I have one ready to go here, so I have the numbers ready. I'm going to pick this one. So the probability that someone was a girl, what did we find out that out from before? 53%, 52.51%, right? 0.5251. The other one was girl given sports. We just did that one. That was the 0.333. Now, are those even close? No. That's almost 20% different. That's not even close. So this is where I said in the other class, if they were within 1 or 2 percentages, I would say that they're probably close enough to say that, yeah, these are independent. And the AP Stats student said, well, we don't really, we would say that they're not equal. So that's something that I think it depends on what you're doing. If you're doing hypothesis tests, or in this case, with what we're doing, I think it's okay if they're a few percentages off. How many? Depends. If you like that sort of thing, if you like gray area where you can argue your answer, take stats. All right? There's a lot of that. Yes?
So we did the other one, like probably sports, that's 0.1, and then probably sports the girls was.
It's like 7% off or something like that. Yeah, it's something like that. So like say.
I was gonna do the decimal, not percent.
Oh, got it. Yeah, if you do it the other way, this one's a lot closer, but it's still like 7% off to me. That's different enough to say, what are we saying? Are these independent or not independent? These are not independent.
Would you say less than 1%?
No, well, it depends on the situation. I mean, we're just talking about some elementary kids in Michigan and whether their gender affects, or not affects, but if there's an association between gender and what their goals are. I mean, I think within a few percentage points, we'd be okay to say that.
So we don't even have to regard the guys in this situation.
No, well, you could do boys compared to boys given any of those categories. You could do any of them, but we chose these because those were the ones that we already calculated. Okay. Yes?
The bottom one gets you closer than the top? Why?
Yeah, the bottom ones, percentages are closer.
Why would that be?
Just because of the way that the numbers work out.
Oh, okay.
But they're still far enough apart to say that they're not independent. We'll just say these. Now, I'm trying to speed things up a little bit here. If this were an AP Stats sort of answer, we would be a little bit more detailed here. I'm okay if you just write not independent, all right, for what we're doing. Like in AP Stats, you'd write something like, because the probability of randomly selecting a girl and randomly selecting a girl, if I knew they played sports, are so different, I would say that gender and goals are not independent. There appears to be some sort of association between these two variables. Something like, right, you're an AP Stats, right? You take your answer and you basically bubble wrap it in a whole bunch of words is what happens. All right. On to the back examples. How are those pumpkin seeds?
Very good.
Good. All right.
That's what I need.
I don't know how you're eating it without water.
I know, I'm so
Like,
thirsty.
yeah,
I
okay.
drink water.
All right. Now we're going to talk just some more. I just threw these problems on to get a little bit more work with some important probability concepts. The first one being, okay, well, take a second to read through the car repairs little snippet there. It says, in 1 year period, 17% of cars need to be repaired one time, 7% need to be repaired twice, and 4% need 3 or more repairs. Now, those are separate things. Like, the repaired twice doesn't include the ones that are repaired once. Those are all separate things. That confused a few people in the other class. Just throwing that out there. Then it says, what is the probability that a car chosen at random doesn't need any repairs? Well, if it needs some repairs, it would fall into one of those three spots, right? So if it needs some repairs, it would be either 17% or 7% or 4%. So what we could do, I'm going to show you a little thing here and say the probability of needing none, meaning none repairs, is the complement to the probability of needing some or at least one. This concept right here is a really important one. Probability of needing none is always a complement to needing at least one. So I'm going to take 1 and subtract then the sum of those probabilities. I'm going to need 1 repair or 2 repairs or 3 or more repairs. I think that's 0.28 if you add those together, right? Everybody do that? 0.28. All right, so then this probability is 0.72. Now, if you're thinking, yeah, but could we just, like, do we really need to write all that? For your notes, I would have this, because that's a really good concept to know, right there. All right, but really, yeah, you can just go, oh, well, if I add those together, it's 0.28, subtract it from 1, you got 0.72. We all go home happy, but the only reason I took the time to write that stuff down is because it's a pretty important probability concept. All right, so let's look at the next one. What's the probability that they would need no more than 1 repair? What does no more than 1 mean?
But not including, or wait, including.
Including 1
Or less.
or 0, right? So we're looking for the probability of none. Actually, I'm going to use the word none again since that's what I did before. Or plus the probability of 1. So the nice thing here is that we already found the probability of none. That's in the last problem. That was 0.72. Plus probability of 1 would be 0.17. So this is 0.89. All right. The probability of some repairs, we actually found that one already. That's the 0.28 that we have over there, right? And actually, saying the word some is the same as saying at least 1. Okay? So we're going to get into that concept down here again. Do you see where it says in this one, at least 1? What I'm going to have you write right here again is kind of pretty much related to that probability we talked about before, or that little concept, that the probability of at least 1 is the complement to probability of none. It's actually the same equation as we wrote up there, just solved for the other probability. Okay? And we'll come back to that one in a second. I just wanted to connect those two things. But now let's look at what's happening in this problem. Consider the auto repair rates discussed in that example. If you own 2 cars, what is the probability that, and then it asks you a couple of different questions. Now, here's the thing. Since we're saying, well, the probability of this happening and this happening, because I have these 2 cars, we need to multiply some probabilities together, right? In order to multiply probabilities together, though, they have to be independent. So I know you can make the argument that because these are both your car, if you're a bad driver and you're like beating the heck out of your car, that might raise the probability of both those things needing more work, right? We're going to throw that. That's getting a little nitpicky, okay? We're going to throw that out the window and just say we are assuming independence. We're going to assume some independence here just so we can do these problems. Otherwise, we wouldn't be able to do these problems, and that wouldn't be any fun. To each his own. All right, so now we're looking for the probability that neither one is going to need repair. So the probability that neither needs repair means that the first one doesn't need repair and the second one doesn't need repair. Well, what's the probability of one of them not needing a repair? That's that 0.72 from up above. So we can multiply it to itself, or just square it. I think that is 0.5184. Pretty sure these decimals are correct because no one has told me otherwise today. Awesome. Okay, the probability that both are going to need a repair, and just need repair means some repair or at least one repair. So that's that 0.28 that we had, but times itself because they're independent, or at least we're assuming they are. That gives us 0.0784. Now we already have C kind of started. The probability of at least one is a complement to the probability of none, and we already found the probability of neither of these cars needing repair. It's this 0.5184 that we wrote here before. So the complement to that is 0.4816. Is my math correct there? Yes. Questions on that so far? All right. Things get interesting here because we bring Mr. Ziegelbauer into the equation. All right, so here's how Mr. Ziegelbauer is handling his final exam. I'm making this up. Don't take this at full account, okay? Mr. Ziegelbauer is going to give you a list of 20 questions and say, study these questions. I'm putting 8 of them onto the final exam. So you study the questions, and out of the 20 questions, you know how to answer 14 correctly. So if 8 of those 14 show up, you're getting 100% guaranteed, okay? Does this make sense so far? There's 20 questions. You know 14 of them. He's putting 8 on there. We want to know the probability that you answer, or it says some student, but let's say it's you, probability that you answer all 8 questions correctly. So the probability that you know all 8. Now, first of all, let's talk about what the denominator should be, the sample space. How many different groups of questions or how many different exams are possible for Mr. Ziegelbauer to put together? How many questions does he have to choose out of? How many is he going to pick? Does order matter? No, he's just putting questions on. 8 questions, no matter how you order them, are still the same 8 questions, right? Combinations, folks. We have 20 questions, of which he is going to choose 8, which I believe gives Mr. Ziegelbauer almost 126,000 possibilities for this exam. 125,970. So now, how many of those scenarios involve selecting questions that you know? How many questions do you know? 14 out of the 20, right? So let's find out how many ways there are to choose out of those 20 questions. How many ways are there to choose the 14? Oh, I'm sorry, said that wrong. Out of the 14 questions that are being chose, how many ways are there to pick 8 of them? You know 14. Out of that group of 14, how many ways are there to get the 8 questions? And it doesn't matter what order is. Choosing 8 out of the 14 you know is that covers all of them, no matter how you order them. I think that is around 3,000. 3,003. So, anybody calculate that yet? You have less than a 3% chance of getting all 8 right, which is pretty small when you think about it. Like when he says, out of these 20, I'm putting 8, and you're like, okay, I know 14. Let's do this. There's less than a 3% chance you are getting 100% on that. All right, we okay at that one? Next, exactly 5 question. I'm just going to forget the probability notation and get right to the fun stuff. Guess what our denominator is? Same thing. We're still, and you could put the 125970 if you want. We're still choosing 8 out of the 20 questions, right? But now we need to figure out how to choose 5 out of the 14 that you know, and then how many questions left are there? If you know, if there's 5 that you know, how many do you not know? That are going to be on the test. 3, right? There's 3 left on the test that you don't know that, right? Okay, so we'll get there. So we got to figure out how to, out of those 14 that you know, how to get 5 of them. But you're not just answering 5 questions correct. You're answering 5 questions correct and multiply. You are going to answer some questions wrong. How many questions do you not know how to do? I mean total, overall. How many questions do you not know how to do? You don't know how to do 6, right? And we're picking 3 out of those 6. We're not picking them. We're just saying this is the number of ways that could show up. So you're answering 5 questions correct, and you are answering 3 questions incorrectly. This ends up being about 0.3178. We're getting there. There's a better chance if you're answering 5 questions correctly. All right, at least 6 questions. If you're going to answer at least 6 questions, that means 6, 7, or 8 correct, right? You're going to get 6 correct, or 8, 7 correct, or 8 correct. So the 6 correct would be kind of like the setup we did before. Out of the 14 that you know, how many ways can we get 6? And out of the 6 that you don't know, how many ways can we get 2? Because you're answering 6 correct and 2 incorrect. That is you answering 6 questions exactly correct. Or you could answer 7 questions correctly. 7 right and 1 wrong. Or you could answer all 8 questions correctly. And none incorrectly, which you don't need that because you're going to do 6 choose 0, which is just 1, so you don't need that. Your denominator is still 20 choose 8. So that would be some heavy calculator work there. You should get about 54.5%, 0.449. 0.5449, sorry. So a little bit better odds there. Okay. All right.